Okay, back to multivariate models, and I changed our week title to be multivariate general linear models to be a little bit more specific. So hopefully that doesn't confuse anyone, but we're on to our second lecture on multivariate GLMs. So no required readings, but this is a statistics book that is helpful, but I don't recommend reading it just if you have a question. Okay, so as we talked about in the previous lecture, in the overview, there are several ways to look at multivariate patterns from a matrix of Ys. And we're going to be starting with linear models, the MANOVA and regression, etc., to test our patterns. And so all of our previous linear models, for example, ANOVA, regression, ANCOVA, etc., we can run as general linear models, and we can do that also with multivariate data. So here's just a refresher table when you have one continuous Y, which is what we've been talking about, and all of the different types of models with one or more categorical X or one or more continuous X and both, what those look like and what we've talked about. But now we're going to be talking about multivariate models where you have more than one continuous Y. And so when you have one categorical X, it's going to be a MANOVA, so multivariate ANOVA. More than one categorical X will be a factorial MANOVA, assuming you do interactions. One continuous X will now be a multivariate regression, and more than one continuous X will be a multivariate multiple regression, and both is a MANCOVA. So this is going to look very, very similar to what we've talked about in the past. We're just going to be now thinking about a matrix of Ys instead of one column of Ys. So we're going to be talking about some Sparrow data. We're going to use that to get through all of these types of models today. And this data is from Bumpus in 1898, where he measured about 136 sparrows after a bad February storm, and half the birds were dead. And so he wanted to know if natural selection, he wanted to investigate natural selection and determine if there was a difference between dead or alive birds. So just so you know, that's the data we're going to be thinking about. And so the data includes sex, age, if it survived, its total length, which is TL, wing extent, AE, mass, WT, beak head length, BHL, humerus length, HL, femur length, FL, tibio-tarsal length, TTL, skull weight, SW, and the sternum keel length, which should be SKL. And so here's just the data we're going to be looking at. And so one thing you want to think about when you have multivariate data is you have a lot of Ys that may not be on the same scale. And so you want to make sure that you can get these values on similar scale so we can start to do appropriate analyses that aren't thrown off by outliers. And there's lots of ways to do this, but we're going to talk about them. But right now we're just going to do a simple one. So if you recall, the data, some are in millimeters, some are in grams, so they're on really different scales. And so one really simple way to scale your data is to just log everything. And so here what we're doing is logging all of our actual Y variables, so TL through the rest, but I'm only showing up to HL here, binding it back with the interesting categorical information, and then viewing it. So now you can see all of these data are on a very similar scale. And so we talked a lot about correlations when you have all of these Ys. So I'm going to show you a couple more ways to sort of look at the correlation values that you have. So one thing that you can do if you just want to look at all of the relationship between all pairs of variables that you're going to be looking at, and you can see this is still on the log scale, you can just use pairs. And so this shows the relationship between all variables, right? Where two variables intersect, that's sort of like battleship. That's where you can see the relationship between those two variables. And here we're seeing both sides of that correlation matrix, but again, both halves of those triangles are the same. And so this may feel overwhelming, and you maybe don't want to plot your data like this. And so you can also try this chart correlation, which I think is really nice. And this allows you to see the trends in your data on the lower triangle. On the diagonal, kind of like SCAT-MAT. It allows you to see the distribution of each of your variables to see if these things look normal or if non-normal. And then on the upper triangle, it shows the correlation value, and you can specify what type. This, I believe, is Pearson, but you can specify the type of correlation you want. And so it tells you if there's a significant correlation or not, but it gives you actually the correlation value between all of those variables. And so you can see these show a relationship, but they're not too strong. And you can also create a correlation table in case you want to be able to print this out for whatever reason. So here you can use the core function to create a correlation table, and we're rounding it to 3 decimal places. And then this little bit of code allows you to hide that upper triangle and print it. And so that can be really helpful. And if you go to that website, there is some extra code for creating a really nice looking table through LaTeX, but it couldn't get it to work in Beamer and Markdown, so I didn't put it in, but you can look at the website for the code, which I'm sure you can get to work in regular R, not in our Markdown. Okay, and so we're going to start with some of our multivariate tests. So we're going to start with MANOVA, and this is used when there's one or more categorical X variables, and sometimes these are called groups, and more than one Y variable. So MANOVAs compare variation within groups to variation between groups. So similar to an ANOVA, but multivariate. And the assumptions of MANOVA are that the multivariate normal distribution of error variance within the groups. And for whatever reason, should you want to test for this multivariate normality, you can use the m.shapiro.test in the mv-norm test package. The MANOVA assumes that you have equal variance. Remember this within your groups, a homoscedasticity, and then also that there's equal covariance within your groups. So a question we could ask with this data that requires a MANOVA is, how does the sex of the birds alter their total length, wing extent, and femur length? So I'm not going to take the full body size data set. I'm going to practice using just a few of the variables in case you should want to do that. And so the code for this is the MANOVA function, and what you do is you c-bind 3 here, whatever columns you're interested, you can c-bind them. And so here we're interested in these 3 columns, so we c-bind those 3 and ask if that's as a function of sex, and the data is sparrow. And then you summarize it, and here we see that sex is significant, so there's a significant difference between male and female birds in this conglomerate set of 3 variables. And I'll note that MANOVA uses Peli's trace as a test statistic, which falls between 0 and 1. You can see Peli between DF and degrees of freedom and approximate F. And so this Peli's trace is then converted to an F statistic, which is why it's approximate. And a larger Peli's value equals a larger F statistic, which is more likely to reject your null hypothesis. With these MANOVAs, you can also see which specific Ys differ with sex using summary.aov and then looking at your model. And this, I believe, is, it's separating out the response of all 3 of your variables, and we know that these sort of co-vary together, so it depends on if you want to talk about individual variables or if you want to talk about them as a whole. So this is sort of, again, one of those philosophy things, but I just wanted to show you that you can do this if you want, but it's sort of turning your data into more of a single univariate response. And so say you want to look at more than one X, factorial MANOVA. This is fairly similar to what we have done in the past and fairly similar to the previous test, but I just wanted to make sure we covered it. So how does, say you have multiple categorical X variables, how does sex and survival of the birds alter their total length, wing extent, and femur length? So again, you can use that MANOVA function, c-bind to the 3 Y variables that you're interested in, and see if that's a function of an interaction between the 2 groups, sex and survived. And so when you summarize this, you'll see there's a significant effect for sex and survived, and there's no interaction. So the male and female birds are different from each other when it comes to these three variables, and the survived and those that lived and did not live are significantly different from each other in terms of those three variables. But it gets pretty complicated to try to actually understand what that looks like. So I'm showing you data, but this is only looking at one of the variables. So this does not take into account the covariation. So I wouldn't recommend doing this for a paper or anything, because right here I'm showing sex and survived with total length, but we also looked at two other variables. But this image just kind of shows that those birds that didn't survive in the yellowish color, they tended to have larger body sizes, and males also tended to have larger body sizes than females. And so it's just a way to sort of get an idea of the direction of your trends, but plotting multivariate data can be really complicated, which is why we're gonna talk about ordination next week. But for now, with these, I just wanted to point out that it can be challenging. And so moving on to multivariate regression. So here, this is used when there's one or more continuous x variables and more than one y variable. So right, matrix of y's. And multivariate regression assumptions include that all the relationships are linear, that they're multivariate normal distribution of the area of variance. So back to that multivariate normal, because we're thinking about more than one y. There's equal variance, again, homoscedasticity, and then there's the absence of multicollinearity, which really just means that that your y variables aren't correlated. And we know that's not necessarily true, right? We know it's very likely that your y variables are correlated, especially when you're thinking about something like size of a bird. Like those variables of a bird, weight and length and wing length, etc., are going to be correlated. That book that I have in the references suggests that they want no correlation, that you should assume that the correlation is below 0.9. And then when we looked at our correlation table previously, all the correlations were lower than that. So we can feel fairly confident that we are not violating this assumption too strongly here. And so one way you could test for multivariate regression is through questions of allometry. So how do body sizes scale? So does the total length of a bird relate to its other size characteristics? So is the total length a good measure for how big a bird could actually be? It's allometry. And so here we are doing a MANOVA, and now we're going to use all of our y variables instead of just 3. So we're going to C-bind all of our variables except for that total length, because we want to know if total length is a good variable that allows for scaling for the whole body size. So could we just look at total length instead of all of these things? And total length is, of course, continuous, which is why we would have a multivariate regression. And so here we see that, yep, total length scales pretty well with the rest of the body size measurements, that matrix of y's. And so there's evidence for allometry. There's a significant relationship between total length and the rest of the body variables. But as I mentioned, plotting this is going to be very difficult because there's so many y's. And so one way you could plot this relationship is you can visualize this multivariate regression with summary variables. And here we're going to use the PC1 principal components 1 axis. I don't want you to worry about this too much. We're going to talk about it. The code is under the hood here in this slide, but we're going to talk about this in ordination. But there are ways that you can pull out one variable which now is a summary variable, PC1, that represents sort of a lot of this multidimensional data as a relation to your x variable, which was total length. And so that's one way you can look at it. And so here you could summarize the data by saying as your total length increases, so does your overall body size measurements. So moving on to MANCOVA. Mancova is used when there's one or more continuous x variables and one or more categorical x variables, and of course, more than one y variable. So Mancova assumptions include that the relationships are linear when for all continuous variables, multivariate normal distributions of error variance within groups, that you have equal variance, there's no collinearity, or no serious collinearity, and that there's no covariation between your continuous x's and your categorical x's. So it sort of adds that extra piece to look at your two different types of x variables. So a question we might ask here is, how does a bird's overall body size depend on its sex, time survival, or those groups, right, that we use for the factorial ANOVA, and its total length, which is covariate. And so sometimes you'll see when you're looking at this in the literature or online, people will refer to the categorical variables as the group variables and the continuous variables as the covariate variables. So I just wanted to throw that out there so you can sort of be prepared. And so our model, again, is the MANOVA, where you bind all of the y variables, y columns that you're interested in as a function of your TL, total length, which is your covariate, your continuous x, and then plus the interaction of sex times survival. And we know before we didn't really see that interaction of sex times survival, so you could potentially just do that as an additive effect if you wanted. I included it here as an interaction, but I mean, you can test whatever you're interested in. And so again, we see that total length has a significant effect on the total length of a bird significantly determines the overall body size. The sex also does, and so does the survival, but there's no interaction. Okay, so again, visualizing this multivariate model is even more difficult because we're starting to have more and more factors to look at. But we can try it again using the total length as our x variable. That's our continuous variable, PC1 as a representation of that huge cloud of y points. And then plus our groups, so we can color and use different colors and shapes to represent the different categorical groups. And so here our orangish colors are the different sexes, are female birds, and the blues are male birds. And for survived, circles are those birds that died, and those that survived are in triangles. And so I tried to, those are, the triangles have the dashed lines. So those that survived have the dashed lines, and those with solid lines did not survive. And so this can be pretty tricky to understand what a significant effect is, right? So the covariate or the total length, that one's pretty clear. So as your x variable total length increases, so does your overall body size. So that one, pretty straightforward. But when we start to think about the different groups, that's where it gets a little complicated. So if you recall, sex was significant. So male and female birds have different body sizes overall. But when you look at this, it's not very clear to say that, you know, male birds are bigger and female birds are smaller. And maybe you could sort of say that, but it also really depends on the total length. And then also that because there's no interaction between sex and survive, this makes this complicated because it looks like there should be, but there wasn't. And then when you look at those birds that survived, you know, at low, survived or didn't, birds at low total length, birds that survive tend to be larger in body size than those that didn't. But as you get into larger total lengths, it's indistinguishable. And so again, there's no interaction. So all you can say is that birds that survived have a different body size than those that didn't. I would feel confident in saying that. And so with that, please complete your quiz 8.2 on Canvas. And this is the last lecture for this week.